Hello, welcome back. So in the last part, we talk about different testing. We talk about unit testing, integration testing, and system testing, and other testing strategy, testing types. Okay, so here we want to talk about how to do integration testing. So after we test the units, how we integrate them together, right? Okay, so basically, so we have two problems. Sorry, we have two problems. The first problem is so how to test the component interaction. So the second problem is to how to determine the optimal order of integration. Right. So we'll talk about how we solve these two problems. Okay. So how we do the integration can have several impacts, such as the form in which we write unit tests, and the type of test tools to use, and the order of coding testing components, and the cost of generating test cases, and also the cost of locating and correcting defect. Okay. So let's look at this simple illustration. Okay. So the objective of integrating testing is to ensure that the components work in isolation and when assembled. Okay. Let's look at this figure. There are many different units, right, in our software system. You can consider each unit is a class in object-oriented programming. Okay, so we have a main class. We have a other class A, B, C, D, E, F. A would depends on class D and E. Usually it means so A would call the methods in D and E, or A would use the class defined in D and E. Okay, like C would depends on F, and main depends on A and B and C. So this is a component dependence structure. So this we will do integration testing based on such a dependence structure. Okay. So here the component D handles the input, and component F handles the output of the software system. Okay. So how do we? There are two questions to ask for integrating testing. First one is how do we ensure a component is effectively tested in isolation? For example, in this figure, so A depends on D and E. How can we test A without D and E, right? That is the first question. The second question is assuming all components work in isolation. We assume A, D, and E all work in isolation. So what types of faults can be expected when they are combined? So mostly they are interface related problems, like wrong method call, wrong parameters. Yeah, let's look at another example. So this is another example of why integration testing is needed, right? So there's the paper towel dispenser and the faucet, they're both tested individually, but when they are combined together, there's a problem, right? Okay. So to answer the question, the first question is how can we ensure each component is tested sufficiently individually, right? So we need something called stops and drivers. First, let's look at stops. So stops is for example, when you test, if A depends on module D, and when you test A, you don't want to depend on D, so you use a stop to replace D. This stop would simulate the functionality of D in a simpler way. Okay. So the stop must be declared invoked as a real module. You need to make a stop class to simulate a real module. It should have the same name as the replace module, same parameter as the replace module, and same return type as the replace module. Okay, let's look at a detailed example. So here, for example, we want to test the function that is depending on the method sumFunc, but we don't want to involve this sumFunc definition unit because we want to keep them in isolation. So we can use a stop to replace the function sumFunc, but we define sumFunc in a simpler way. For example, here we just define integer, print some information, and return the integer. So that is a stop. Okay, so this stop can be used to replace the actual function, and it can be used in the testing of the dependent unit. Okay, so these are some common functions of a stop. So first is normally we display some print or log or trace message. We also display or print the past parameters, and we return a value according to the test objectives. For example, in this example, we want to have an integer 42 return, so we just return as integer. So this return values can be formed from a table, from an external file, or from like some other heuristics. Okay. Let's look at this example. In the main function, so there is an if branch, right? If x is greater than 0, we call two functions. If x is not greater than 0, we call another function, right? So there are two possible paths, right? The first path is from 1 to 2 to 3 to 4 to 5 to 7. This is the first path. If we want to test this path, so we want to make sure x is greater than 0. How can we ensure that x is greater than 0? So we need to make sure return value of a is greater than 0, right? So, but here, when we test this main function, it depends on the module that defines a, but a is in another module. We want to keep it in isolation. So we need to use a stop. So here, we will use a stop to return a value that is greater than 0 to test this path. Okay. If we want to test another path, so we'll make another stop for a such that it returns a value that is not greater than 0. Okay. Another tool we need to use for such isolation is drivers. For example, we want to test a function a, but how to test a? We need some driver to call a to invoke the function a, right? So this is what a driver does. So let's look at this example. So actually, we want to test the function sumFunc. So here we use a driver. Here we use a driver to call the sumFunc. So this is a driver. The whole class, the whole method is a driver. Okay. Driver is similar to our unit test setup part, right? You always need a driver to call a function. So basically, these are the definitions of stops and drivers. So after we define these basic techniques to test the different components in isolation, so we can combine them together. We can combine these different units together to have integration testing. So how can we combine them? There are different strategies. Big bang strategy, top down, bottom up, and sandwich strategies. So we will talk about each of them in detail. Here, we want to also compare them in terms of different criteria. The first one is the ease of fault localization. The second is effort needed. And the third one is the degree of testing of modules achieved. The fourth one is a possibility of a parallel development. So whether the development and testing can be in parallel. Okay, let's look at first big bang integration. So big bang integration is that we test all components as a whole. Here, in this simple example, we just test all the modules. We combine them into a whole system to run a test. So that's a big bang integration. There's no incremental strategy. So after we test each unit in isolation, then we test the whole system. That's a big bang strategy. Advantage of big bang strategy is it is convenient for small stable systems. For example, you write a small program for your assignment, and you test all the different classes, and you just test the whole system together, right? That's very easy. Disadvantage is it doesn't allow parallel development and testing, right? Because in order to do the testing at the last step, you need to finish everything, right? So you need to finish all the development before you can do the big bang testing. Okay, and fault localization is difficult because you test everything together. If something is wrong, you don't know where is the root cause, and it's easy to miss interface faults because you don't test all the interfaces. You just test them all together. Another way is to do incremental testing. Instead of test all the units together, we do it one step by one step. So the first one is top-down strategy, top-down integration. So what we do? So we first test the highest level. Then we test the lower level components until all the components are tested. Okay, like in this example, we would first test the main unit. So here, when we test main, but main depends on others, right? So remember, we need to use stops or drivers. We need to use stops, right? We need to use stops to replace A and B and C, right? Then we test main and A and B and C together. Then we test main and A and B and C plus D and E and F together. So that's a top-down strategy. It's possible to have a different order. For example, so we want to test the critical components as early as possible. We want to test the input-output components as early as possible. So we can do this order. We can first test the main, then main and A and C. Then we test A and C and D and F. And finally, we test all of them together. Still a top-down, but different order, right? Okay. So there are some advantages and disadvantages of a top-down integration. So first one is a fault localization is easier, right? Because we do it incrementally. When there's an error, we can localize it easily. Normally we don't use drivers because we go top down. What we need is stops. And it's possible to obtain early prototype because we test from top to components to the lower components. So we first test the whole system, but with stops. And testing can be in parallel with implementation. For example, after you implement the main part, you can test main. After you implement the main and A and B, you can test main and A and B, right? It can be in parallel with implementation, okay? We can have different order of integration. And we can find the major design flaws first. The major design flaws usually happens in a higher level, so we can find those major design flaws first. But there are some disadvantages. The first one is we need lots of steps, because when we test the high level units, so it depends on lower level units, but lower level units are not available, so we need many steps. And also potentially reusable components may not be adequately tested because they're at the bottom of the hierarchy. Okay, so this is a top-down strategy. The next strategy is a bottom-up strategy. It's a reverse order. It's also an incremental strategy. First, we test low-level components. Then we test the components that depends on the low-level components. And we go higher and higher until we test the top component. Okay, so in this example, what we can do, we test D and E and F separately. Then we test A and D and E together, right? And also we test C and F together. And also test B, and finally we test all of them together. So it's from low level components to highest level. Okay, here look at, so when we test, for example, when we test D and test E and test F, because we need something to call them, to invoke them, so we need drivers to replace A and C, right? Advantages. Also, fault localization is easier because it's an incremental strategy. There's no need for steps because we go from the lower level component to higher level component. What we need is driver, right? And we test reusable components thoroughly because we test them first. They are usually at the lowest level. And also the testing can be in parallel with implementation, the same idea. And also, we also can have a different order of integration. But there are some disadvantages. We need a lot of drivers because we test a lower level components. So we need drivers to call them, to drive them. So the high level components are tested the last. There might be a problem because the high level components usually indicate some major design problems, right? So we don't have an early scanning tool system, and we don't have a prototype because we test the highest level at the last. I think there's please go ahead, Jean. Ask your question.
Could you clarify the difference between a stub and a driver?
Okay. Let's look at let's look at this example, right? So go look at the figure on the left. Like A depends on D and E, right? So you can imagine A is a class, D and E are another two classes, and A would call a method defined in D and also call a method defined in E, right? So when we test D, right? When we test D, we need to run D, right? So we need to call D. So we need to have a driver to call D, right? Is that clear for driver?
Okay, yeah.
And for stop is if we want to test A, right? If we want to test A in isolation, especially in top-down integration, we test A before we test D and E. In this case, D and E are not available. So, but A should depends on D and E. So we make a replacement. We make some dummy D and E. Those are stubs. Those are simulation of the functionalities in D and E. Is that clear?
Yeah, it's clear. Thank you.
Okay. So this is a bottom-up strategy. And another is a sandwich strategy, which is a combination of a top-down and a bottom-up strategy. So basically, we can first we can do top-down for top levels, and we can do bottom-up for the bottom levels. And there's a middle level. So we first run the middle level. We test the last. Okay. For example, here in this example, so we test D, E, and F, and also main. We test them first, right? Then we integrate them together. We test ADE, we test CF, we test main ABC, and finally we test all of them, right? That's a sandwich. We test the top level and the bottom levels first. Then we do integration. And finally we test all of them. That's a sandwich integration, okay? Okay, so we look at 3 strategies. Sorry, some loading problem. Okay. Okay, so, oh, I don't have this. Sorry, I just accidentally stopped sharing. 1 second. I'm sharing again. Can you see the slides?
Yes.
Okay.
Yes.
Yeah. So this basically this slides is just summarize the different advantages and disadvantages of different testing strategies. Okay, so we already covered them, so you can go to details from the slides on Moodle. Okay. So next we will discuss white box and black box testing. So these are the 2 testing strategies usually. So imagine when we test a car, right? There are 2 ways to test a car. One way is we don't see the inside of the car. We just drive the car and to see whether the functionalities are correct. So this is a black box test, or it's a function test. We test the functionalities. Another way is we test. We see the inside of the car, right? We check each component whether they're correct. We check the combination of the components, and we can see what's going on inside. So this is a white box testing, or sometimes called glass box testing. This is structural testing. We test the structure of the system. So it's the same for the software testing. We have a black box testing and white box testing. So black box testing is based on the software description. Is based on software requirements. We test the software against the requirements. So we want to cover as much specified behavior as possible. But we cannot cover the issues related to implementation details, which are not reflected in the like a behavior. Okay, for white box testing, it's based on the code. We don't look at the behavior. We check the code. We test whether the code are running correctly, whether the code are implemented correctly. So we want to cover as much coded behavior as possible. It cannot reveal errors due to missing paths. For example, if we don't implement one behavior, so we cannot test it in a white box testing because we don't. It's based on the code, but the code is missing, right? Okay, let's look at the details of the two types of testing. For first, white box testing. So white box testing requires a full knowledge of the system. Including the source code and the documentation. Okay. So it examines the internal calculation paths. So we can use white box testing to test the data processing process, the accuracy of the calculations, and the qualification of the software, because we examine the code. And there's one way to evaluate the white box testing is to look at the coverage. So in white box testing, we want to cover as much code as possible. So this is also always defined as a coverage. Let's look at this example. Here, you look at the code on the left, and also look at the figure on the right, which actually is an illustration of the code, the flow graph of the code, right? So if we want to test this piece of code using white box, so how can we test it? So we want to increase the coverage, right? So we want to test all the paths. So we want to run the software and also make sure the test would cover all possible paths, right? And there are 3 ways to evaluate the coverage. The first one is the line coverage, and also have a branch coverage and a path coverage. So let's look at each of them individually. So line coverage is about cover all possible statements. So here in this example, so how many tests do we need to cover all the statements, to cover all their lines? So we only need one test, right? So this test would first would go through the path A, and then C, then D, then E, then G, then H. In this way, you cover all the nodes or all the statements or all their lines. So we need only one test to cover all the lines, right? This is the line coverage. How about branch coverages? The branch coverage would cover all the possible branches. So we need basically we need the first test is from A to C to D, then E, G, H. So we cover the right branches, right? This is the first test. The second, we want to test the path from A to B to E to F. So we cover the branches on the left. This will cover other branches. We use 2 tests to cover all the branches, right? But what if we want to cover all the paths? We would need 4 test cases to cover all the paths. Because the paths can be from the first branch can be, one combination is left of the first branch and right of the second branch. Another would be the right of the first branch and the left of the second branch. So they have different combinations. So to cover all the paths is very difficult to achieve. It's even impractical for many programs. So normally we cannot ensure a very high coverage of all the paths. So the easiest way to achieve is our line coverage. Then maybe a balance between them is a branch coverage. Okay. So 3 ways for coverage in white box testing: line coverage, path coverage, and branch coverage. Ideally, we want to cover all the paths, but it's impractical. So in fact, we use other alternatives like line coverage and branch coverage. So this is about the white box testing. So how about black box testing? So we don't look at the code in black box testing. So tests run the code with given input and they compare the results with the expected outputs. Doesn't consider the internal code. It's less expensive than white box testing because we don't want to test all the paths or the lines. We just want to test the behaviors, right? We just want to test it based on the requirements. So we must specify the input and output data. But there are many possible combinations. The fact is we don't need to test all of them. So how can we choose the test cases? So there's something called equivalent classes. So we will discuss what is the concept of equivalent classes, okay? So we cannot test all the possible input values, right? So because it is impractical, so we need to we need to sample test cases from all the possible input values. So this one strategy is to divide the possible inputs into groups. Within each group, the input values are similar. So they are called equivalence partitions or equivalent classes. So we want to choose test cases from each of the equivalent partitions or classes. Okay, let's look at this figure, right? So this figure, so left part as represent the inputs, and the right part represent the outputs, and we feed inputs to the system, and it generates the outputs. So for inputs, we can partition all the possible input values into some equivalence partitions, as shown in the figure. Also, for the outputs, we can have other equivalent partitions. So after we have such equivalent partitions, so we can just choose a small number of test cases from each partition, right? So we don't need to choose all the possible values because they are very similar. Okay. So how do we choose equivalent partitions? And how do we choose test cases from each equivalent partition? We will discuss. So first, for each partition, how do we choose the test cases? So this is a 3-way rule, which are the happy way, the marginal way, and the exceptional way. For the happy way, we select test cases near the middle of equivalent partitions. For marginal way, we select test cases on the edge. For exceptional way, we select invalid test cases. Let's look at example. Okay. For example, the valid input is a month number from 1 to 12, January to December, right? 1 to 12 is a month number. The input is a month number. So what can be the equivalence classes? So one way is to divide into 3 partitions. Of course, the first partition is from 1 to 12, right? Is a valid input. Another partition is from any number that is equal or smaller than 0, right? Another partition is any number that's equal or larger than 13, right? So we have 3 partitions. And the 3-way, right? 3-way rules. The first, the happy way, the valid values, the leader middle, which is like 6, 10. They are like valid inputs, the reasonable inputs, right? And also the marginal way, which is border values in the valid partitions, like which is 1 and 12. Those are the borderline values. And we need to choose another is an exceptional way, the invalid values, which is 1 from each invalid partition, which is minus 10 from first invalid partition, which is 100 from the second invalid partition. So this is an example of how we choose equivalence partitions and how we choose values from equivalence partitions, right? So usually this not only just one input, we should consider more than one input. So we need to consider combinations of equivalence classes. But if, for example, if there are 2 inputs and each input would have 5 equivalence partitions, then there would be 10 combinations. But if there are like 100 partitions and each of them would have on average 5 equivalence partitions, so that would be the value is too big for us to test, right? So we cannot test all the combinations. So what we can do, right? So first we need to make sure that at least one test is run with every equivalent class of every individual input. For each individual input, we should cover every equivalent class, right? And also we should test the combinations where the input is likely to affect the interpretation of another. If 2 inputs, they are related, we should test their combination. So this is how we choose combinations of equivalent classes. Let's look at this example. So one valid input is either metric or US imperial. So there's 2 measurements. So we can have equivalent classes of, we have 3 equivalent classes. One is a metric, one is a US imperial. And there's another partition which is the invalid input is other, right? And another invalid input is maximum speed. It can be from 1 to 750 kilometer per hour, right? Or 1 to 500 miles per hour for different metrics. So the valid equivalent classes can be from 1 to 500, and from 501 to 750, right? And the invalid values can be any value smaller than 0 or greater than 750, right? So these are the partitions. So we have 2 inputs. So how can we choose the combinations of them? First rule is to make sure each equivalent class of each input is covered, right? Then we test the related ones. for example, we would choose such combinations. For metric, we choose one from 1 to 500, which covers one partition from each input. And we also consider the US imperial from 1 to 500, right? We'll also consider metric from 501 to 750. And we choose a US imperial from 501 to 750. So here we should consider more. These are just some of the test combinations. We should also consider invalid inputs. The value smaller than 0 or the value larger than 750, okay? Let's look at a complete example. So this example is from a textbook. So we consider a software that calculates the price for a training room, right? The price depends on 4 variables. The first variable is the day of the week. The second is the member or non-member. The third variable is the time of entry, right? At 2 time slots, 2 possible time slots, and the age. So they have a different price for different ages, like like younger than 16, or between 16 and 60, and greater and from 60 to 120, right? So what are the equivalence classes? What are the test cases? We consider equivalent classes for each input variable. Okay, let's look at what are the equivalent classes. For day variable, first, what are the valid classes? What are valid equivalent classes? First one is from Monday to Friday, right? Is equivalent class, equivalence class, and Saturday and Sunday another equivalent class. And the invalid classes can be any other string, right? How about the valid value? The happy way can be Monday, Tuesday, or any other day, right? Or border value, because here is only the 5 days. You can, so one way is to consider Tuesday and Wednesday as the value, and Monday and Friday as a border value. But also you can consider like Monday or Friday as a value already. So you don't need a border value, okay? For invalid class, you can choose any string, right? As a test. For example, you can choose MOX as the invalid value. For Saturday and Sunday, so your value. For example, Saturday. For member, you have also 3 partitions. One is a member, another is a non-member, and an invalid class is any other string, right? And you choose a value and invalid value, right? Entry time, we have a valid partitions for its 2 valid time slots, and also have 2 invalid classes. One is earlier than the equivalent valid classes. So another is any other string value, right? So so we choose the value. For example, for the partition from 6 o'clock to 19 o'clock, we can choose a value of 755, right? And for border value, we choose both 6 and 19, right? Okay. And also similar for the ages, right? So these are the equivalent classes and how we choose a valid value, border value, and invalid values. So after we have these equivalent classes, so how can we choose the test cases? We need to make sure that we cover each equivalent class of each input, right? Right here. like first we cover all the value cases. We cover the value cases for each input variable. I think because so here we have 3 value cases because one because the age variable has 3 value equivalence classes, so we have 3 value cases. These 3 value cases will cover the value, the equivalent classes of each input value, of each input variable. And second, we cover the value border cases. So we cover all the, for each input variable and each equivalent class, we cover the value border cases. And we also cover invalid cases here. So here in total, we have 15 test cases. So after we have this 15 test cases, so we will design test scripts to run the 15 test cases and check whether the result is the same as specified, expected. Okay, is there any question about equivalent class or white box testing? Okay, so we talked about white box and black box testing. So let's compare them. The first, if you see a plus, which means an advantage, if you see a minus, which means a disadvantage. For black box testing, it checks the conformance of the system with the specification. It is easy to scale up because it doesn't look at the internal code, so it's running more efficiently. However, it depends on details in spec. So we need to make sure our specification is very clear. And it doesn't tell how much of our system is being tested. We don't look at the internal structure of the system, so we don't know whether it's well covered. So for white box testing, it allows for the measuring of the test coverage. It also is based on control of data flow coverage. So we can make sure that we can evaluate like how much of the system has been tested, how much of the paths or lines are tested. But it doesn't scale up well because it's very inefficient to cover all the paths or the branches or the lines. Okay, and you cannot reveal missing functionality because if this functionality is not implemented, we cannot discover it by looking at the code, right? Do we need black box testing or white box testing? Or do we need both of them? The answer is yes, we need both of them. Because missing functionality cannot be revealed by white box techniques. And white box testing is hard to scale. And also unexpected functionality cannot be revealed by black box techniques. Because in black box techniques, we only check the requirements. But if there are additional functionality that is unexpected, we don't even know, right? So we need both of black box testing and white box testing. And finally, so for what types of testing can we use white box testing and black box testing? So we can use black box testing for all kinds of quality requirements. For example, we use black box testing for correctness, for availability, for reliability, for flexibility, portability, for other attributes. But for white box testing, it can be only applied in a few cases, like to test the correctness, to test the maintainability correctness, to test the reused software correctness test. All these tests are corrected. These tests, so basically, it is to test whether is to run the code and to test whether the input value can produce an expected output value. That's a correctness test. Okay. White box testing cannot be used to test other attributes, such as if you want to test the speed. If you want to test the speed, you can just run the software system and to check the speed, whether the speed meets the expectation. So you don't need to look at the internal code. So that's the job of the black box testing. Okay. Okay. So far, any questions about testing strategy and white box testing and the black box testing? Okay, if no, let's have our second break. So let's how much time do we have left? 3:45. Let's come back at 2:30. Okay. Thanks.